Welcome to the captivating realm of ionic compounds. These compounds are more than just chemical curiosities. They are fundamental to countless aspects of our daily lives and the natural world. Imagine a story where tiny charged particles called ions come together to form solid structures with unique properties. Let's embark on an adventure to explore the formation, properties, and significance of ionic compounds. At the heart of ionic compounds are ions, which are atoms or molecules that have gained or lost electrons, resulting in a net electrical charge. These ions can be either positive, cations, or negative, anions. Cations. Positively charged ions formed when atoms lose electrons. Common examples include sodium, Na+, magnesium, Mg2+, and calcium, Ca2+. Anions. Negatively charged ions formed when atoms gain electrons. Common examples include chloride, Cl, oxide, O2, and sulfate, SO42. Ionic compounds are formed through the electrostatic attraction between oppositely charged ions. This process typically involves a metal and a non-metal. Electron transfer. Metals, like those in groups 1 and 2 of the periodic table, tend to lose electrons, forming cations. Non-metals, like those in groups 6 and 7, tend to gain electrons, forming anions. Bond formation. The positive and negative ions attract each other, forming a strong ionic bond. This bond is the foundation of the ionic compound. Crystal lattice. The ions arrange themselves in a regular, repeating pattern known as a crystal lattice. This structure maximizes the attraction between ions and minimizes repulsion, resulting in a stable solid. Ionic compounds have a set of distinctive properties that arise from their strong ionic bonds and orderly crystal structures. High melting and boiling points. The strong electrostatic forces between ions in an ionic compound require a lot of energy to break, resulting in high melting and boiling points. For example, sodium chloride, NaCl, melts at around 810 and boils at 1413. Hard and brittle. Ionic compounds are generally hard because of the strong forces holding the ions together. However, they are also brittle. When a force is applied, the ions shift and like charges repel, causing the compound to shatter. Electrical conductivity. In solid form, ionic compounds do not conduct electricity because the ions are fixed in place. However, when dissolved in water or melted, the ions become free to move, allowing the compound to conduct electricity. This is why salt water conducts electricity while solid salt does not. Solubility in water. Many ionic compounds are soluble in water. Water molecules surround and separate the ions, allowing them to dissolve. This property is crucial for many biological and industrial processes. Ionic compounds are all around us, playing vital roles in various aspects of our lives. Table salt, sodium chloride, NaCl. Perhaps the most well-known ionic compound, table salt, is essential for seasoning food and preserving it. It's also critical for biological functions like nerve transmission and muscle contraction. Calcium carbonate, Ca3, found in limestone, marble, and chalk. Calcium carbonate is used in construction, cement and concrete, as a dietary calcium supplement, and in antacid tablets. Sodium bicarbonate, baking soda, NaHCO3. This versatile compound is used in baking to make cakes rise, in cleaning as a mild abrasive, and in medicine to relieve acid indigestion. Magnesium sulfate, Epsom salt, MgSO4. Epsom salt is used in bath soaks to soothe muscles, in gardening to provide magnesium to plants, and in medicine as a laxative. Beyond their practical uses, ionic compounds are fundamental to various natural and industrial processes. Biological functions. Ions such as sodium, Na+, potassium, K+, calcium, Ca2+, and chloride, Cl, are crucial for nerve function, muscle contraction, and maintaining fluid balance in the body. Industrial applications. Ionic compounds are used in manufacturing glass, ceramics, and cement. They are also essential in chemical processes like electrolysis, where compounds like sodium hydroxide, NaOH, and chlorine gas, Cl2, are produced. Environmental impact. Understanding ionic compounds helps in addressing environmental issues. For example, controlling the pH of soil and water often involves adding compounds like lime, calcium oxide, CaO, or gypsum, calcium sulfate, KSO4. Ionic compounds are a testament to the remarkable ways in which atoms interact to achieve stability and form structures with unique and useful properties. From the salt in your shaker to the chalk on your blackboard, these compounds play a crucial role in everyday life and the natural world. By understanding the formation and properties of ionic compounds, we gain insight into the fundamental processes that shape our world and improve our lives. So next time you sprinkle salt on your fries or use baking soda in a recipe, remember the incredible journey of ions and the strong bonds they form to create these essential compounds. It's a microscopic marvel with a massive impact.